ahead and so right, basic housekeeping. One, the meeting is being recorded. Basically, so it'll get uploaded after the talk. A couple days later, it'll get uploaded to the Scudic Institute's YouTube channel. And then, if for those of you who are online, feel free to ask your questions via chat. And I think otherwise, I'm going to turn it over to Bill to introduce today's speakers.
Welcome, everybody, and I'm glad we could all be here today. Back in June of, what was that? 2021, yeah. We had a pretty intense storm here where we got, over 4 inches of rain in probably about, less than 2 or 3 hours, and caused some major flooding in a lot of areas in the park. And so as a result of that, we were really kind of hoping to employ some of our longtime research partners from USGS to help us deal with the increasing precipitation events and the vulnerability of streams to erosion and how that intersects with infrastructure like trails and culverts and roads and everything else. So we started this project shortly after, and this is we're already in the second year of implementation. So we're lucky enough to have the project team here, the whole shebang, and Megan and Ian and Nina from USGS, and we were out in the field this morning looking at some of these sites on the ground, and they're going to kind of give you the progress report on where we are now. So take it away.
Sure. Thank you, Bill. So as Bill mentioned, we'll be discussing kind of our current progress with the stream flood vulnerability assessment. And so just to reintroduce the team, sorry, technical difficulties here.
Maybe spacebar. Yeah, the slide's not changing to next slide. I'm wondering. Maybe do that, yeah. There we go, okay.
Perfect, great. So my name is Megan McAllister. Besides my obvious prowess as an IT person, I'm also a hydrologist and do a lot of hydraulic modeling of crossing structures.
Yeah, I'm Ian Armstrong. I'm also a hydrologist and do a lot of surface water modeling projects.
I am Christina Labrie. I'm a physical scientist. I handle a lot of the GIS aspects of this project.
And I'm Pam Lombard. I'm a supervisory hydrologist in the New England Water Science Center, and I sit in Maine. And this all sort of came out of this conversation we had to develop this. We'll talk more about it, but this 5-part concept proposal. And so this is really parts 1 and 2 of that. And really excited that we got this great team working on it, so we can take it away.
Sure. Lastly, we've also listed Adam Bentham, who is a hydrologist who really built some of the framework for looking at the geomorphic assessment of the streams. And so we're really thankful for his involvement as like kind of a mentor for this project at this point. So back in June 9th, that storm in 2021, we really saw a lot of damage due to that high intensity rainfall and seeing how it kind of impacted various structures. And, not only is the infrastructure itself damaged by high intensity rainfall events like that, but you also see, deposits of things like carriage road materials in the natural landscape because of that. And so the goal of this project was to be able to assess the vulnerability of those stream reaches within the park to erosion, And then also to be able to assess the ability of crossings, so bridges and culverts, to be able to pass larger storm events. And this kind of fits into a general framework that us at USGS and you all at National Park Service kind of work together to create. So right now we're working on task 1 and task 2, which is assessing the ecosystem vulnerability in those stream corridors and also assessing the infrastructure vulnerability. And hopefully from there, in the future, we'd also be able to collect, better high stream flow data, being able to, look at how do we replace those culverts and design those replacements, and then also taking into account the impacts of climate change on those structures. And here in Acadia, we really do have, such a unique landscape, being, having all the miles of coastline, as well as, large ponds, and a really large stream network as well. So on the screen here, I have the NHD data set of the stream network that we were kind of looking at in the beginning of the project. And just the methods that were used to develop the NHD don't take into account kind of the granularity of the topography here. And so it was really important when looking at the stream network to be able to have something that really represents what's actually going on. And with this project, we're really focused on MDI specifically.
So with this, we felt that the need to update the NHD was very important for the project and how our data is going to work. So you can see here, the red line indicates where the NHD lines are, and I have pointed out a few areas where you can see that when we use something like a geomorphic index as a channel indicator, and we use a flow accumulator raster that shows where channelization should be, the NHD falls out of that in many areas that are important. There's the circled area at the top left that kind of shows where there possibly would be 2 culverts, but the NHD just kind of goes in the middle and doesn't really pick any area there. So something like that is where we would support the GMI and the FAC layer and put some breach lines in there. We would start the stream at the top with a seed point, and we'd be using some tools to kind of recreate where this line should go based on our FAC and the GMI. So we did an extensive editing and review process. We wanted to make sure that the streamline that we were creating followed the DEM. So we used tools, elevation-derived hydrography tools that were customized for national parks because we wanted to follow the 0.1 square kilometer drainage area to kind of avoid a lot of the smaller headwaters, because with a 100-meter FAC length, we wanted the analysis and the next steps that we're going to follow through with Ian. We're producing enough valid data for where our stream should go. And you can see here that when we used breach lines, some of them that we placed where culverts were placed based on data that we had received where culverts should be. Automatic placement of breach lines were a little bit off from where they should follow the GMI and the FAC, so they were manually edited. And then also there's another blue line at the bottom there that shows where an inlet should be for a stream to flow into a larger water body. We want to make sure that those lines are a little bit easier to follow, a little more natural. So those were some editing that we did, and we also had some in-house review process to make sure that what we're doing overall had some other eyes on it to make sure, since it was pretty in-depth. So in the results, you can see here on the right, this is the updated hydrography, which if you can kind of remember from before what the NHD looked like, very limited and very inaccurate. On the left is the first picture that we seen with the red still being the NHD. The blue line is the new EDH lines, and those follow more upstream than the NHD does in a lot of areas, and definitely follows the channelization that is evident from the DEM. And then it makes it definitely more comprehensive and a full stream network that we need in order for the analysis steps that we're coming up next.
All right, so that was going over updating the hydrography throughout the park, and now I'll be talking about task one, and that is assessing ecosystem vulnerability to erosion throughout all the streams in the park. So task one, the goal was to assess which streams or what part of the streams throughout the park will be most susceptible to erosion during high flood events. And so the goal of this, in order to map out the entire island in an efficient manner, mostly just using LiDAR data, was to create an erosion vulnerability index map, which contains geomorphic factors that are most correlated to erosion throughout the park. And so how we do this is we're going to take variables that are seen in the stream power equation in order to predict areas with erosion potential. The stream power equation, signified by omega, is a unit of energy that is expelled by the water on both the stream bed and the stream banks. And so a stream section with higher stream power is going to be putting more energy against that stream bottom and the stream banks, whereas an area with low stream power is less likely to erode and has less energy against those stream banks. And so, rather than trying to solve this erosion equation, the stream power equation, our vulnerability index is going to examine the primary drivers in this equation that we can readily measure through LiDAR. So when we look at the stream power equation, we can see that it contains rho, which is the density of water. And so we can take that out because that's a constant. There's also gravity in there, so we can take that out because that's also a constant. And so Q is discharge, and that is usually bankful discharge. And so we can measure this using built regression equations developed by Pam for the state of Maine. So we can readily calculate 2-year bankful discharge. S is channel slope, and we can measure that using LiDAR and the updated hydrography that Nina talked about. Bankful width, which is denoted as W, is really hard to measure accurately through just LiDAR alone. Usually it requires extensive field work. And so rather than measuring bankful width, we decided to input another metric, and this is topographic openness. And this estimates the bank slope and amount of incision within a section of stream. And so going over that topographic openness, incised channels, as many of you might know, are channels that are over steepened banks, and they have a positive feedback loop of continuing erosion. This is because you can find the higher magnitude flood flows within just the channel itself, rather than that water being able to go out and expel over the overbanks and kind of dissipate naturally. When you have a very incised channel, you're putting all of that water from that flood straight into the channel banks, and it's just going to keep eroding those banks down. And so they tend to carry higher sediment and pollutant loads from eroding banks that generally degrade stream habitat. And so how we're going to estimate this topographic openness, or this amount of incision, is we'll use the topographic openness tool developed by White Box Tools that's able to measure the amount of incision or the openness within a section of stream. So you can see that section with very small banks has a high openness, whereas on the right, a very incised stream has a low openness. And so if we take our stream network and we calculate these different metrics, you can see here with channel slope, you can see you have a lower channel slope down in the downstream components of the stream, whereas in the high waters and in the headwater areas, you have a high channel slope. So high channel slope is colored more warm in this case. For channel openness, you can see these highly incised areas in the LiDAR contain a very low openness, which is colored warmer, whereas areas with kind of wide open meadows and low banks contain a higher openness, and so that is colored cooler. And finally, the bankful discharge. We set delineation points to calculate the drainage basin, use precipitation values, as well as percent storage in the basin to calculate the actual bankful discharge for sections of streams. We couldn't do this for every 10-meter section of stream, Rather, we decided every 0.1 square kilometer increase in drainage area, we're going to calculate the bank full discharge. It takes a lot of processing time to do so. Once we calculate the bank full discharge, we divide the value by drainage area. Therefore, we're normalizing everything by drainage area and really just looking at the amount of storage within each section of stream. So during a flash flood event, a stream with a low amount of storage is most likely going to receive way higher amount of surface runoff rather than a stream section with a lot of storage or a lot of upland wetlands. And so combining these three parameters together, slope, topographic openness, and bank full discharge, we add all these values up and we rank them within each other. So ideally, a stream segment with the highest erosion capability will rank on a value of 3. However, for our entire network across the island, our highest value is a 2.7. Our minimum value is 0.24. And so you can see generally the areas with the highest erosion potential, which are colored in warmer colors rather than the cooler colors, are mainly located on those steep gradients, those steep hill slopes, usually around Sargent Mountain, Cadillac Mountain, and whatnot, kind of going into the lowland areas. Whereas you can see areas with primarily marshland and fairly flat have a low erosion potential. We were going to do a difference in DEM map to compare 10 years of a DEM from 2010 and a DEM from 2021 to see if we can tease out areas that have received erosion within the past 10 years. However, you can see this DEM difference map from 2010 to 2021. You can actually see some of the flight paths that they ran to measure the DEM. And quite frankly, the amount of error involved within this difference map is way higher than the resolution we're trying to go for within the stream banks. And so we decided that we are most likely going to have to remove this from the analysis just due to the amount of error. However, if we look at specific sections with high erosion potential, you can see here, I believe Cadillac Mountain is on the left right there. Here's a specific trail. It might be Murphy Trail or something along those lines. Murphy, yeah. So this ranked as one of the highest spots in the park with erosion potential. And you can see it's very incised, it's very steep, and it has little to no storage in the upstream headwaters. And so during a flash flood event, those banks are going to be highly susceptible to eroding and collapsing. I actually haven't visited this yet, but it seems like just visually it's been receiving some erosion. Across the saddle there on the north side, I forget what trail this is as well. Yeah. Okay. Yeah. So yeah, you can see that. Yeah. Also very incised, very steep, containing little to no headwater storage. And so this also ranks one of the top areas where future erosion is most likely going to be seen, especially along that trail network. And then finally, as many of you know, and we visited a year back, the Maple Spring Trail, as well as this is the Hemlock Trail on the right. You can see up in those headwaters up there, very brightly colored. These are ranking some of the highest areas in the whole park of future erosion potential. And I believe you guys, on the left trail there, there's ongoing, that trail is currently closed. There's ongoing repair work being done. The trail on the right, I know you mentioned there's also some damages being done as well, and maybe some repair work. So overall, just these highly incised areas where water is not able to spread out. You contain all that energy within a deep valley, especially these kind of flashy headwater areas with no storage. These are really the areas that you're going to see a lot of erosion taking place. And let's see what else. Oh yeah, I got one more area right here. I forgot to circle that area. Shoot, I'm not sure where that is, but again, yeah, another area along a trail. So yeah, so we have the preliminary results there. We have some other analysis that we want to do, but yeah, so that's where we're at with task 1 so far. So.
Sure. Yeah, and these two tasks really do work together and impact each other. But the second part of the current project is assessing the vulnerability of infrastructure. And so to do that, what we're looking to do is to compile a culvert inventory, have a lot of attributes from all different data sources, be able to compute the flood risks at all of those crossings, and also develop a way to prioritize where you would replace structures due to that flood risk. And so looking at like what we'd include for the compiled infrastructure data, things like just the location itself, what are the crossings made of, is it on a trail or is it on a carriage road or a motor road, what is like the fish passage, are known fish species in that specific stream, any maintenance history that we can include. And so pulling all of that together, we're also, compiling it not only from your data sources, but also other things that are available from like the state of Maine or the Nature Conservancy, or our own data sets at the USGS. And so we were really grateful last year, we come here around the same time of year. We got to go to Maple Spring Trail, as you saw in Ian's part of the presentation, and being able to directly get information from you all is like the most helpful thing for moving this project forward. So thank you. And so based on all those different data sets, these are all of the crossings that we identified on Mount Desert Island. These include areas outside of the park as well. So filtering that down, if we look at just the crossings that are within park boundaries themselves, that takes us down to 1291 different crossings. But we thought it was important to also address culverts that were, directly adjacent to the park, or in areas that were directly upstream or downstream on a stream that also goes through the park. So we went and manually included those to be included in the flood risk analysis. For example, this area here, we wanted to still be able to look at that stream and look at those different crossings, because if something happens there on the bottom, that's still going to impact the park, even if it's not directly owned by the park. So to do those flow computations, we were originally thinking we were going to be able to just use USGS stream stats, be able to do a batch process and get all of those different flow values just using the website. But since we've gone and updated the hydrography, that allows us to be able to use those same regression equations that are in stream stats, but be able to do them with an updated stream location, and be able to kind of map those drainage areas ourselves. So if you see on the left in the yellow, at this particular point, that's the drainage area that you get from stream stats. And then in purple, you can see the drainage area that was outputted by our tool. And you can look at the different flows and you can see that they're relatively similar, and be able to kind of verify that this makes sense as a process, and also just having just like better data from being able to update where that stream network is. So in doing so, and looking at this updated stream network, another thing that we were able to do is look at the locations of the crossings. So with some of these data sources, such if they're from like something like the NAC, that is a database where those locations come from intersecting NHD with different roads layers. And so if you have one of those crossings, that location might not actually reflect reality. So being able to use the specific updated stream hydrography and have a suggested updated location for the crossings can also just kind of give us better information to work with. Another thing that we noticed when we were looking at this updated stream network is locations where we have a pretty good idea that there's probably a stream in a location where it's crossing a road or crossing a carriage road or crossing a trail. And we can see that there are no culverts identified in our compiled database. So we also want to identify those points and be able to provide that to you all. So that we can see, maybe this is a place where we should include that crossing in our database, and later on be able to collect data such as like the sizes and the materials and start to kind of build those out. So that's something else that we're looking to provide. And during our visit here this week, we'll also be visiting a couple of those sites and seeing if what we're finding on our GIS desktop analysis makes sense when compared to what we see in the field. So once we have flows at these updated locations with the updated stream network, we also are going to have to figure out what is the capacity of the existing culvert to be able to pass flows. So we did some analysis of some existing ways that people go about this. And basically, we're going to kind of start off with looking at making those calculations based on inlet control. So kind of just standard equations from Federal Highway, and applying those based on the attributes that we have in our compiled culvert database. So with having, our heights and widths, knowing what the shape of a crossing is, knowing the material, and knowing the fill above the culvert up to the road, and what type of inlet there are, that gives us some different data to kind of start off with. So for instance, knowing that this is a circular corrugated metal with a projected inlet coming out of that slope, we know that it's matches what's on that bottom line. I know it's a little bit small, but that gives us some coefficients that we can throw back into that the Federal Highway equation. So just kind of moving that equation along, we're looking to find the capacity of the culvert to convey flow. And to do that, we need the cross-sectional area of the inlet that we're able to calculate based on the dimensions. We need, again, just the height of the culvert from the dimensions, the headwater depth, the Y coefficient, which was on the table on the previous slide, based on the culvert material, and the way that the inlet type, and the shape. We'll have us just kind of a standard slope correction factor, 0.5, unless the inlet type is metered, culvert barrel slope. And so that's something that we can get, kind of have an estimation from if it's not available in the database itself. We can get that from Ian's analysis of what the slope is of the stream going into it, and kind of make some estimations based on that, or based on kind of the upstream watershed, what the average slope is, and use that as an input into this equation. Again, see a constant from the previous slide, and then just a general unit conversion factor that will be applied to all of them. And so then we can go take, an outputted capacity, and then compare that capacity to the various different flood flows, and be able to identify whether or not that specific flood flow is being able to be passed by that particular culvert. And so this is kind of what I was alluding to, having the ability to not only just say what the capacity is, having that as an attribute, but also in our culvert database, having whether or not it conveys each flow. And from there, being able to identify what risk the culvert is at for flood flows. So on the right, I have a screenshot from the Nature Conservancy's Flood Risk Explorer, where they did kind of a similar study that doesn't, contain all of, 1,300 of the culverts that we've identified of wanting to study, but using that kind of similar framework and coming up with something that will allow you to kind of look at different culverts and know what the general risk is. And another thing that we want to include in our culvert database is being able to pull some of the stuff from task 1 about the stream and being able to apply that. So having, at a crossing, you'd look at a specific culvert and you would want to know, what's the channel slope for that particular section? How open is it? And like, how does it rank on the erosion vulnerability index? So pulling that all together.
Yeah, so the next steps of this project is to combine the task 1, the erosion capability of the streams, with Megan's task 2. So having those culvert locations on the same map and seeing if stream segments with high erosion vulnerability are abutted against culverts with low capability to pass flood flows. Those would be areas that you guys really want to focus on. So those are kind of the next steps. We also want to create a quality checking method for both task 1 and task 2, make sure our data looks correct and that there aren't any apparent errors in our analysis. And then we also want to create a plan for the metadata structure and actually releasing our data to the public and the final products. So the final products that we will be publishing through this project is the updated hydrography network, stream network map. The stream erosion risk map, which is what I talked about, the culvert vulnerability data release that Megan talked about, the DEM difference map. I don't think we're going to be able to include that confidently in this analysis, so we're going to be taking that out most likely. A decision support dashboard tool, so all our results will be published onto a public site that anyone could go on and access and be able to look at all of this data presented in this analysis. We're going to be publishing a scientific investigations report and also a geo-narrative. So timeline and budget, we are a little bit behind time, but we are right on with budget. Right now, we should be undergoing the data release for task 1 and task 2. However, we're just kind of undergoing the final steps of the analysis. So a little bit behind, but we're very confident that we're looking good in terms of the overall goal. Next year will be mostly comprised of writing up that scientific investigations report and publishing our data. And that concludes the end of our presentation. And I appreciate you all watching, and we'll take any questions that you guys have. So, thank you.
Also, I just wanted to thank you guys. That was a really good overview. And one of the things I also wanted to mention, and Adam would sort of often bring this up as he conceived of this project, is that it's a pretty broad overview. It's a desktop analysis, and it's really looking at the prioritization of culverts relative to each other as opposed to absolute amounts of erosion. I mean, the culvert analysis is more with real flows, but I would say it's more of a prioritization tool than like quantifying amounts of erosion. So I think that was clear in the presentation. I just wanted to say that explicitly.
Yeah, that's a good point.
Is there, in thinking about like some of the places that are steep, some of them are just on rock.
Mm-hmm.
And some of them are on like. So is there any substrate like in the analysis?
Yeah, so that's a great point you brought up. From the moment we got here and started looking at we went to what was that? Deerbrook. We went to Deerbrook today, which ranked very high on our analysis, very steep, highly incised. But a lot of that stream is just pure bedrock, including the banks as well. So in reality, it's probably not going to erode for a very, very long time. So that is one big limitation of this analysis, is that there really is no field work. So we aren't able to, through LiDAR alone, we aren't able to tease out if the banks are comprised of soil or bedrock. There are superficial geology maps that are published, but quickly looking at them, it looked like it was just very broad. areas with even just a few feet of soil will be very susceptible to erosion, but those areas might just be labeled as bedrock, under the map. But that is the next step that we're going to look at is, unfortunately, at the resolution of this project, without any field work, we really aren't able to know, what these banks are really looking like. So yeah, I mean, it would be a great addition to this project to be able to go out and actually map out what areas have that loose soil banks that's collapsing versus areas with just solid bedrock. And then another thing we are going to do is this erosion map is sort of biased towards those steep headwater streams, which is mostly bedrock because it's on the sides of those mountains. We might group these results by drainage area. So we have an index for drainage areas below this value, which includes all the headwater streams. But then we also look at all of the streams off of the mountains that mostly have soil banks and whatnot. So yeah, it's a great that's truly one of the biggest limitations of this project is that
And my other question.
Yeah.
I'll let everybody else. I know we talked about this before when you were in here last time, but I forgotten how we were handling it. But so when in that big June storm, like a lot of the damage wasn't actually at crossings, but it was like in ditches or just trails, right? Like because a lot of our trails are actually in the streets, and so it was just like the lot. So is there going to be a place that we capture that? Is that just going to get captured just in the kind of like the steep, in the steepness, and then we'll have to just identify kind of areas where the trail's in that stream, or because the stream is in a ditch, alongside of a carriage road.
Yeah. So really in this, we're only looking at streams with a drainage area of 0.1 square kilometers or greater, which is mostly all of your actual officially named streams. We don't really have the resolution within the LiDAR to be looking at these small kind of runoff streams or like hill slope, runoff streams for that matter. Our stream segments are divided into 10-meter lengths. So that's the smallest kind of 30 feet of stream is labeled individually with its own erosion index. But we really don't go any smaller than 10 meters in length. And yeah, we're mostly just looking at streams that are I feel like a lot of the streams are probably ephemeral, but most streams that are, show up under the topographic maps and whatnot.
Is it possible to get to overlay where these streams that you mapped are either in infrastructure or adjacent to it?
Yeah.
So where they exactly overlap with like trails.
Yeah, absolutely.
Right adjacent to roads.
Yeah.
Or carriage roads.
Yeah, we can absolutely do that.
That could become part of the.
Yeah.
Because that would be
Pieces of
erosion
mobility, yeah.
with
Yes.
the
That matters.
undermining or whatever the thing is.
Yeah.
even if it's not crossing.
I mean,
Apply a risk assessment
think
to
if
trails that are within a certain area of those streams that
Right,
are.
or the carriage roads or the motor road.
Yeah.
Yeah. I mean, if I have shape files of your
'cause you can see
your
them
trail
here, you can see how
network.
close they are.
So right here,
Well,
yeah,
it's the
doing.
same thing.
Yeah.
The trail is the
Yeah.
stream.
Yeah.
Yeah.
So I think finding a way to automate them, that'll be the trick, is finding a way to sort of automate that.
Yeah.
Because it's such a large.
Yeah.
array.
But we could do a spatial search from the stream network to the trails
Divide
or
the
whatever
trails the same way.
infrastructure you want.
Divide
Yeah.
the-
We could absolutely do that. That's a
Just
good
snap
idea.
it to the section of the trail that's on.
Yeah.
We saw a lot of that even on our first walk today.
Yeah.
There was a lot of the carriage road coming across it or
Yep.
and those,
Yeah. The areas that are walled up next to it where the flow can't really escape, those roads are taking a beating for sure.
The other thing though is that continues to be a real struggle is how small can we go on the drainage areas? Because, so the regression equations, only going down to 0.2 square miles. So we're outside the limits of the bounds of the regression equations. We're outside the bounds of the limit of the hydrography tools that we have. So we're really right at the edge of all of those tools. And so, which is hard here because those are the areas of interest. But that's another thing we're sort of identifying, and can we get better flow numbers? That's, another piece of this, and developing those tools. But yeah, we went back and forth on that minimum drainage area size, because we know how important some of those areas are, but we were bumping up against, really, we're already over the limit for this.
Our watersheds are tiny.
Yeah. And some of the areas that you're most concerned of, so yeah, that's another limitation.
It's not like Maple Spring is that far from the.
No. A lot of the 2-year flood flows are literally 1 CFS, that it's producing. When it's running. It's crazy. So, yeah, that's.
So those would be some of the areas where if we did more data collection in the future, we could get more information on how to, so I mean, if there were some that were in that smaller category that we think are priorities.
And that's even, so 0.2 square miles is the limit of our statewide equations. We only got Outer Creek here. So, we're not basing, and the hydrology is different here than the rest of the state, as we all know. So, we're not basing it on very much. I mean, all of these studies were really limited by the hydrology. Continually bump up against that. Could we get us, a crest stage gauge network? That would be an inexpensive way to get more coverage of peak flows. We have the low flow network, but the errors are unknown at that scale, for here, and so I think that's going to be a challenge for any of this stuff that we even, the next steps on this concept proposal that's what we're bumping up against.
Yeah, great questions.
Other questions?
Yeah, you mentioned at the beginning that you were also trying to take into account the effects of climate change. How are you, what are you using there? What kind of factors are you using, or what kind of predictive methods?
So that's kind of in this framework that we've set out. That's kind of the 5th step. So after looking at updating our peak flow data, and so to really include the impacts of climate change, especially with kind of my part, and then also with your stream flows that you're calculating, your 2-year flood flows, it would be having updated regression equations for those flows that are based on changes to the climate. So having updating kind of those atmospheric inputs, and then that updated precipitation data, and then plugging that into our regression equations, and having updated flows, and being able to look at the culvert and look at that capacity, and think about what's the 100-year flow right now, but also what's going to be the 100-year flow in 50 years, and does that culvert have the capacity to pass those flows in the future?
And I will say, or climate change, everybody is interested. We're all interested in it, but we don't know what hydrology is right now here. So it's really hard. I mean, projecting it is hard everywhere, but if you don't know what it is now, we're that's where we have to start somewhere.
Yeah.
Not to harp on it. We'll have the same conversation.
But I will say with this erosion vulnerability map, really, rather than looking at the amount of flow going through these streams, we're normalizing everything by drainage area. So really what we're looking at is the amount of storage that's within the headwaters of these streams. Regardless of what that flow back value actually is, this map should be able to capture on a normalized scale what stream reach is, regardless of climate change, just based on pure topography, what reach is based on those stream power. Based on that stream power equation, what reaches are most susceptible to future erosion. So rather than Megan's part, which looks at the actual flows going through the culverts, this really should stand against the test of time until you update that LiDAR data set again. So I guess that's a benefit of this index map, is that regardless of how much rain you're going to receive, the areas with the highest erosion capability are going to be the same, I guess.
You'll also be able to get with incorporating climate change, those precipitation values. You have the changes of those reflected in that stuff.
Yeah.
As well.
Yeah.
Overall, I do like the relativity of
Yeah.
this because there's a lot of because there's so much sort of nuance of superficial geology, but then where are there, clay deposits underneath that, and it just goes on and on.
Oh,
and
yeah.
We do have a lot of very localized expertise of understanding that's where the trail takes a bend like this and
Right.
goes over this
Yeah.
sloppy part that always kind of goes like that.
Yeah,
And
yeah.
with the relativity, I think pull some of that in.
Yeah.
And I mean, this is just looking at the very broad scale. It actually, I was kind of impressed at how much it looked like I would have expected.
Yeah. Yeah.
Which is great.
Yeah.
So I think that's, I don't know, that's pretty exciting for me anyway.
Yeah.
It does seem like that sort of element can be very useful because for instance, it is erosion potential, right?
Mhm.
It's not necessarily this is where it has eroded and this is
Right.
where it's going to erode.
Yeah.
We didn't think Maple Spring would wash out either. That's
Right.
big chunks of rock.
Yeah.
And
Yeah.
so,
Yeah.
but to understand sort of that relativity.
Yeah,
is really
yeah.
key in as we think about the application into management, I always do get concerned when we get a list of here's the top 10 culverts that need to get replaced. And then, 10 years down the road when climate change is a little different, then we're okay, we'll throw that list out and start again. But if we can actually start to think about these in here's a place as we overlay these different aspects.
Yeah.
I think hopefully it's something that's going to be really useful.
Yeah. Yeah.
So, thank you.
Yeah. No, thank you. Yeah. I'll just, reiterate, actually, trying to model actual bank erosion taking place within specific areas is just, it's incredibly difficult to do. So, like you said, this isn't saying how much it's going to erode. We aren't trying to quantify actual values. This is just if you look at only the park and the stream reaches in the park, what areas are more susceptible than others. Yeah. So, yeah.
And I really also want to highlight the hydrography. I mean, I think that's one of the biggest tool outputs out of this project, honestly, and having real streamlines in the right place. And it would be nice to get your input on those as well, because you have so much localized knowledge, but that'll just be in a data release that anyone can access at that point after, we've all had a chance to review it.
I was gonna ask about that, and can that be used to update the NHD? Are you guys planning on trying to push that out?
Long story.
It's not standard,
No, it's a long, we do have some folks in our office who are working on that.
Yeah.
And going into it, so we could submit it.
Yeah. That's all.
It's a stream stats.
Well, I know, exactly, yeah.
There's a lot of naming conventions, a lot of attribute tables that need to be used on all of those sections.
Yeah, the NHD is very bad. It's so it's horrible. Yeah. So.
Yeah, I mean, we had sort of incorporated that, but then piecing it out, that we just thought really taking the time, and so that even is more useful than this DEM comparison, and putting our time into getting that correct seems like a valuable option.
Yeah, it's not just the DEM or the flow accumulator and the GMI, but a lot of times I would have to just go into an ortho and say, okay, what is really going on here? Because you see so many possibilities. And then if it seems that what needs to happen is the stream needs to be higher than what the NHD had previously, because all the other features were there, then that's what we did. Because the numbers are there, and you
But
just
at some point,
have to manually look
for
at it.
that internal review will be probably.
Are there ways to measure, so the DEM to measure erosion didn't work, right?
Mhm.
Are there, if we want to, are there other ways to measure it? I guess, is fieldwork the only option, and what would be the best way to look at that?
Yeah, I mean, I guess, flying a new LiDAR survey, which is field work essentially, but that would be a possibility. But really, I think along surveying a cross section in the field and resurveying that year after year would probably be the best method of trying to actually quantify the amount of erosion taking place. But if you're trying to do island wide, certainly would need to do a really high resolution flying of a new LiDAR data set, I think would be the best way to go. And then, yeah.
But you know, we do have places where we've done cross sections year after year, where we measure stream flow. That could be an interesting, you know, if people are getting it in the same place, that's one place where we actually have that data. It's very limited.
Yeah.
We don't, our INM, regular INM data don't do that, do they?
Yeah,
Outside of
that's
the-
part of our
Oh,
discharge
Yeah,
is,
yeah,
is
actually, we could-
So in all the spots.
it might be interesting to look at that, just to overlay that on top. There's just one little piece of real.
Yeah.
that's 15 some odd years worth of data, but
Yeah. If people are getting in the same place, I know they
Yeah.
measure in different places with different flows, for small streams.
yeah, some places are better than others, but.
Yeah, and I think the problem with the LiDAR is, you know, you flow it, the improvement in technology over that time span is such that it's hard to say that that's all due to erosion, as opposed to
Yeah.
new technology. And also, it doesn't do really well on steep
Yeah.
banks or like anything where you have to have that, you know, a single line, like a levee or a dam or a bank. It's always averaging, so it's just.
Yeah, just the amount of the amount of error within that analysis is way too high to be confidently saying like this received erosion within the
For
next
this
10 years.
scale.
For this scale, yeah. So it's really tough. I mean, people will do pre and post landslide analysis with a pre-landslide fly of LiDAR and then a post landslide fly of LiDAR, and it needs to be just very exact, and the points really need to line up. So it can be done for sure. Yeah. And there's many ways you can do structure from motion. People could go out and take pictures of the banks like every month or something. And you can actually, there's programs that can calculate the amount of erosion taking place as well. So but field work is really, the best way to go about it. So.
Which would have also been better for substrate as well. To know exactly what's there, because there's some banks we're looking at and it's solid rock and you know that's a wall that's not coming down.
Right.
Other places, there's a lot more that will create some deposit and more erosion downstream.
And Megan, how much were you able to incorporate like the past history, you know, that I know you talked to Keith about that a little bit?
Yeah. So we have, you know, different data sets from you all. And so, you know, in the Culvert database, having extra like note spaces. So sometimes, you know, it's not something that we can necessarily, you know, quantify as a specific, you know, numbered attribute, but it's something that we can include in the notes, and having indications of specific events that occurred, or, you know, in the case of some of the culverts, especially like on the carriage roads, they'll be marked as like cyclic maintenance, you know, every year. And it'll just be something that's like, you know, that that's being looked at every year when the carriage roads are being maintained. So there's different notes like that, depending on the data available. So definitely a lot more, you know, information on like some of the carriage roads more than like, you know, smaller trails, but yeah.
If we started adding like retention and dispersion on the outlet side of some of these culverts, how does that change, or would that change the way the model works, or is this something we'd have to know? Some of the flashier stuff, that's what we're talking about doing, is to try to slow the water down on the outlet.
Sure. So that won't impact that specific, you know, capacity of the culvert to pass flows, but in terms of the impacts to them, in terms of what actually happens with erosion, definitely would make a huge difference. So in the culvert database, we have whether or not like the outlet is like perched. So with a lot of them, it'll have that measurement. It'll be like the outlet of the culvert is perched 2 feet, you know, above where the stream is going afterwards. And so that's an area where, you know, you would definitely, you know, think that you're going to have, you know, higher velocities going there and being able to, you know, keep on increasing how perched that is over time. And so that's something that we could definitely, you know, include as an attribute, whether or not there's been work done directly downstream, but it wouldn't go into the calculations themselves.
And part of that is because of the assumption of inlet control. And we played around a little bit with that, like, do we have to assume that they're all inlet control, or can we get a little more complex? But we just didn't have slope on enough of them that making them anything but inlet controlled means that anything downstream is not gonna play into this particular equation. So it's not gonna show up, even though, they might in reality not be an inlet control culvert. We just had to make that assumption for this analysis. That's the data we had, that's the level of data we had. But that would be something, so in this larger concept proposal, these were steps 1 and 2, and then we had, more stream gauging information. And then the next step was more of a culvert design tool. And we were doing a project like that in Massachusetts, where you could get sort of preliminary culvert designs. And in that case, then you would be bringing in more of that stuff. What type of culvert is it? What's the slope? And so that would involve more data collection if we don't have that level of data on these culverts.
Right, that would be incorporating more what's happening. You'd have multiple cross sections. So you'd have a cross section both at the inlet and outlet, and then you would also be taking into account an approach and exit cross section, and being able to look at those different specific water levels. So
Are you looking at is that what they call the invert pipes?
Yeah.
Yeah.
Culvert,
Yep.
actual
That's how you get at the
those.
slope. Yeah.
And that's what my question is. So like Cadillac has 21 new culverts. Is it as simple as just adding the new dimensions and then update? And then how would we go about doing that in the future?
Sure. So with this particular project, we'll be releasing the culvert database, to the public, as well as you also. It'd be something that, hopefully would be easy for, either us or for you all to update, with any additional points. And the actual calculations themselves with the culvert capacities are relatively automated. Since there are 1,300, not doing that by hand or on a calculator. So it'd be something that would be pretty quick to be updated.
And all of a sudden, so we're in year 2. We're sort of, in the middle of the analysis, and really open still to your ideas, like adding that, relative vulnerability close to infrastructure. That's something we could easily look at and see how hard that would be to incorporate. But either in terms of products or usefulness, like your outreach or any of that, if you have ideas for, we can't change the scope of the project, obviously, but we still have a little bit of flexibility in terms of what's most useful. I mean, this is a tool for the park, and so if there's things that you're looking at and you're saying, like, this would really help, or this not so much, we're really open to that.
Yeah.
There's 1 more year, is that right?
Yeah.
And then this is an NRPP project?
Yes.
Yeah, we should talk about, this is when we should be talking about the next.
Yeah.
We already are.
Okay.
Not for this specifically, yeah. And also, when we were talking, NRPP is having some tough times right now, so if we can get more creative and other ways to,
Sure.
do some of this work.
Find different funding sources.
Yeah.
There's the cask and other things we could look at.
Yeah. I'm gonna put you on the spot since you're here and you're so gracious to spend the time with us this morning, but from your perspective in the trails, maintenance and planning and things like that, what do you think would be the best? What's on your wish list or the top of your wish list anyway?
Well, it's funny because I've gone through my head like the kind of specific questions that come up to us when we look at an area that's been damaged. And, think of that process we went through with Maple Springs. We had a lot of experts there kind of looking it over and talking about all the different treatments all the different things we could do. Some of the stuff we talked about this morning, do we actually just bug out and move the trail? Is there a way to build it back? And so I think some of the questions that will probably need to be answered more often in the future will have to do with what kinds of structures could potentially hold up in a given environment. That I know that's beyond the scope of the project that you have right now, but it seems like one of those really important decision points is like moving something, rebuilding it. And anything that any any part of this that could point us in a better direction in terms of that part of the decision tree came up again, even on Ocean Path, that was a ocean damage rather than stream, but like, it certainly, that's a question that's kind of becoming ever present, I think, in the current era, is like, can we just build it better and make it survive, or do we have to like really think about moving things or bringing in a whole different way of constructing things? And I've been trying to connect that with like the project you guys are doing, and I'm not sure if they are or not. I'm just throwing that out there because I know that I think that's one of the places where we find ourselves a lot at that decision point. So it's the culvert thing, you guys are specifically studying crossings, and in some ways that's a little bit of a simpler problem. You've got how much flow it is, what size crossing you need, and that kind of thing, than the adjacent feature problem adjacent to a high flow area, whether it's a stream or a floodplain, and what's happening to that feature all along the area, and how does that get treated? And again, I'm not sure what's really in your scope or what could be, but those are just a few things I was thinking about.
Yeah, I think last time we were here, we talked about Maple Stream, all the different things that go into your decision tree, and obviously we're not getting at how much it costs and what the historical value is. So yeah, there's parts that are not going to be included in this. But we were sort of like, with the erosion vulnerability index, we're looking upstream and downstream, like what is going to impact potentially a culvert, and what a culvert blowout might eventually impact downstream. So there was a little bit of that into play, but it's not as sophisticated as all of your thought processes that are going into this right now. It's like, how do you model the human brain? But if you do think of something that, like, what's a question that I'm stuck on that this prioritization could get at, because otherwise, you won't use it, right? Unless it helps you actually move forward in one of your hard decisions.
Right.
Or something you could bring to the larger group and say, this doesn't include your cultural part or your financial part, but it does say relative to other culverts, where we might spend our time.
Yeah, and solving any part of it becomes really useful.
Yeah.
Because when you have those complex problems, it's like, okay, well, at least we know what to do about this part of it, or we have this part of the answer. You can usually build on that to get to the next parts of your answer. The problem is when you're looking at it, you're like, wow, I don't know the answer to any of these questions, And I think what you guys are doing is probably going to help us quite a bit with part of that issue, which is like.
But yeah, if you're thinking about when you're at a meeting or when you're presenting this to the public, like what information in what form you could use best, and if you come to that a little bit more, give us a call.
Yeah, thank you. Yeah, I think a number of us will be, now that we know a lot more about what you're doing, what your process is, we'll have probably
reach
be in
out,
touch again with.
Seriously, that'd be great.
Well, before we get too long, because right now, like this year is the time to think about all of that before we start, doing some of the products.
We just started doing QR codes on our gauge stations. And those will not only give the public information to what's going on at the gauge station, but projects that are associated with that. We could potentially do the same for trails for this project, so people can understand the impacts, the historic changes, because you said for Maple Spring, like you have people that are regulars there and they don't want that trail removed. There's a QR code there, so we get information. Public outreach is a little bit easier that way if you link it to the project that we're doing, as well as some historical factors that you guys have for those trails, and that may help bring funding in as well.
Sorry.
I was just gonna say, that's a great idea, having the QR codes, because it's unobtrusive and compact and everything else, but it's something you could easily kind of get right on a trailhead or on a trail map, or, a number of different places.
Oh yeah, the entire project can be within, on one QR code.
Like that geo-narrative, whatever we come up with.
Exactly.
Really explain it to people.
Yep.
Some of the hard decisions that you're.
And then will we flag the trails that are most vulnerable based on, the index that we have set, then those are ones that maybe they're like, oh, let's check this out, we heard that this, like, it's pretty bad, and then they check it out and know what the implications are, but you guys have these questions that you need to answer, do we move it or do we rebuild it?
Well, thank you guys
Yeah.
very much for all the time, and the work is awesome. I was super impressed with the updated right stream mapping that was, and I know, this is great, I think this is going really well, so thank you, really appreciate all the work.
Incredible.
And just for those of us here, the next Tuesday, Amanda Pollock will be talking about the Juneteenth and the history behind that observation the day before actual Juneteenth. But thank you everybody online, and this will be up online before too long. Thanks.
Please reach out.